jumping back in here with the electromotive force, which is something we actually discussed in the last video, although we didn't call it that. What the electromotive force is it's the cell potential. It is the voltage of the voltaic cell. It's essentially the potential difference from the anode side to the cathode side of the cell, or to go again with the analogy from the last video, it's the height of that waterfall. It's how far, in terms of potential energy, does the electron get to fall, going from one side of the cell to the other. So the larger the cell potential, the more power that is supplied by the cell. And this is something that I'm sure you at least know in one way or another, just because you know that a 9-volt battery can shock you pretty good if you stick it on your tongue, which I would not suggest. Whereas a AA, which has 1.5 volts, it doesn't have nearly as much power. But voltage is not everything, by the way. It's just that is one part of what makes a battery useful, is its voltage. The amperage is also very important. But anyway, when we're talking about cell potential, we're usually going to write it as E cell. So the capital E is the potential, the electrochemical potential, and then cell is just saying this is the electrochemical potential of the cell that we're looking at. And usually, and actually for our purposes always, it is going to be measured in volts. There are other very out in left field type units that can be used to talk about electrochemical cell potential, but we are always going to use volts when we are working through problems here. Volts is a derived unit. It is not an elementary unit to the SI system. It is derived from the amount of energy that a coulomb of electrons will experience, the energy difference that a coulomb of electrons will experience when they move from one side of a voltaic cell to the other side of the voltaic cell under a 1-volt potential. So if there's 1-volt potential difference from one side to the other, a coulomb of electrons will experience 1 joule worth of energy difference. So thinking back to voltaic cells and electrodes in voltaic cells, typically in battery systems like this, the anode is made of a metal that is oxidized, and the cathode is made of the same metal that is being produced by the reduction. So you have some kind of metal cation that is in the solution, and whatever metal that is in solution, you have a stick of metal that is the same metal made up of the cathode. So if the redox reaction we are running involves the oxidation or reduction of an ion to a different oxidation state, or the oxidation or reduction of a gas, sometimes we have to use what's called an inert electrode. And essentially what the inert electrode is used for is if, for example, we're going to have reduction involving hydrogen gas. Well, we can't have a stick of hydrogen gas. It is physically impossible to have a piece of hydrogen gas to stick into a solution. So instead, we need something for the reaction to take place on. We need some kind of an inert surface where the reaction can take place and still be in the solution. And so that's what an inert electrode is for. Usually they're made of platinum or some kind of similar metal. They're not cheap, as platinum is quite expensive, but that inert electrode allows these other types of reactions, these other redox reactions, to occur while not actually participating in the reaction itself. One of such reactions, half reactions, that we are going to see quite a bit is what's called the standard hydrogen electrode. And the standard hydrogen electrode is the C level for electrochemical half cells. Now, what do I mean by that? Well, if we read at the top here, we cannot measure the absolute tendency of a half reaction. We can only measure its relative tendency to another half reaction. Essentially what this is saying is, to go back to our analogy of a waterfall, you can't really talk about the height of a waterfall based on only one side of the waterfall. You can't just look at the top of the waterfall and say, oh, this is this height, without having something else to compare it to. There has to be a comparison to talk about the height of something. Now, whether you're comparing it to the bottom of the waterfall, which is something you could do, which is what's usually done, or you could even reference the height of the waterfall versus sea level. This is something we do with like the height of mountains. There always has to be something to compare it to. Nothing has an absolute height. Like even you have a height, but that is comparing the bottom of your body, the bottom of your feet, to the top of your feet. There's a starting point and ending point. You're comparing one side versus the other. How far does it go from one side to the other? There's always a comparison there. There's something that you're comparing against. And it's the same thing here with half reactions. You can't talk about the absolute tendency for a half reaction to occur. It is always in reference to something else. How likely is this reaction to occur relative to this other half reaction? And so that other half reaction that we were always going to be comparing to is this standard hydrogen electrode, or SHE, as it's sometimes called, the standard hydrogen electrode. So this is our sea level. This is what we're going to compare everything else to. We're going to say this half reaction is more or less likely to be reduced as compared to hydrogen being reduced in the standard hydrogen electrode. And so just like sea level has 0 elevation, our sea level is going to have 0 volts. That is going to be the standard reduction potential for our standard hydrogen electrode, and everything else will be relative to that. So this is kind of reiterating some of what I just said, but the standard hydrogen electrode reduction potential is defined to be exactly 0. Standard reduction potential, compare the tendency for a particular reduction half reaction to occur relative to the reduction of H plus into H2, because that is the direction the reaction goes in when it's being reduced. This is under standard conditions, so if you don't remember that, it's 1 molar, 1 atmosphere, and well, we don't have a pure solution here, but that's mainly what we're looking for. Is we have 1 atmosphere of H2 and we have 1 molar H plus in solution. That's the main thing we're concerned with. So half reactions with stronger tendencies towards reduction will have positive values of the standard reduction potential, and half reactions that are more likely to be oxidized than the standard hydrogen electrode will have negative values. And no matter what half cell we're looking at, the standard reduction potential is always going to be the same value as the standard oxidation potential, just opposite in sign. But just rest assured, we're not really going to look at the standard oxidation potential anymore. It's a thing, people use it, but we are going to focus on the standard reduction potential, just because it'll make our lives easier to only have to think about this one versus having to think about both. So, what people did was they said, okay, if this is going to be our sea level, let's compare everything to that. And so they took that standard hydrogen electrode, which is this side here, and they put it in electrochemical cells with every other redox half reaction they could think of. Every other half reaction they could find, they would put it and compare it to the standard hydrogen electrode and see what voltage they got. See what the cell voltage was. And that gave us this nice table here of standard electrode potentials, standard reduction potentials. Because everything here is shown as being reduced. So everything above right here, because this is the standard hydrogen electrode right there, Everything above this is a stronger oxidizing agent, which means, and again here the nomenclature gets wonky. Because it's a stronger oxidizing agent, that means it's more likely to be reduced, which means the stuff up here likes being the cathode. And then everything lower is a weaker oxidizing agent, which means the stronger reducing agent, which means that it is most likely to be oxidized. Because again, weird nomenclature, the reducing agent is the thing that is oxidized. So therefore, we are more likely to find things down here that want to be the anode. Does not necessarily mean they have to be the anode, but the stuff down on this end of the table would more like to be the anode than the stuff up at the top. All right. So, a spontaneous reaction, if we're going to start comparing these half reactions, we just want to pick two and see if we can make a reaction that works. A spontaneous reaction is going to take place when a when a reduction half reaction. So again, the reduction would be the cathode. Again, the consonants go together, vowels go together. When the cathode half reaction, the reduction half reaction, is paired with an oxidation half reaction, which is the anode, that is lower on the table. So if we have a reaction that's taking place, and our oxidation, our anode, is lower on this table, what that tells us is that that reaction, as it is written, is spontaneous. The voltaic cell will work. It will give us some power. We can run our jukebox with it, or whatever it is that we're running, turn on the light, run our cell phone, whatever the case may be. If we have an anode that is lower on the table than the cathode, we will get a spontaneous chemical reaction. So, just as an example here, we have two different half reactions. We start off here with both of them shown as being reductions, because that's how everything looks on our table here. Everything is written as a reduction. So we have copper 2 and zinc 2 being reduced. In one possible combination here, we have the copper being reduced and the zinc is being oxidized. Notice here that the zinc is the opposite of what's written up here. So we have the zinc being oxidized, the copper being reduced. And so if we check the values here, copper is our, let's see, that would be our cathode, and the zinc is our anode, because again, this is being reduced, and so that is the cathode, this is being oxidized, that's the anode. And if we find those on the table, here is zinc, and copper is not there. I know that looks like the right one, but this is copper 2 plus going to copper plus. We want copper 2 plus going to copper. There it is. So if this is our cathode, and this is our anode, then this process is indeed spontaneous, and that's what we see there. We're telling us that it is spontaneous. If we had it flipped the other way, if the copper was being oxidized and the zinc was being reduced, then it would be non-spontaneous. By definition, if it's spontaneous in one direction, it is not spontaneous in the opposite direction. We talked about this in the last chapter. We can take this a step further, though. What if we don't just want to know if it's spontaneous or not? What if we actually want to know what is the voltage of this cell? Not just will it happen, but how much juice will I get out of this? How much power will my cell have? Well, if we have something like this is a pretty straightforward cell here. We have a zinc as our oxidation, so zinc 2 plus and zinc metal. And then for our other side of the voltaic cell, we have the standard hydrogen electrode. To find the actual cell voltage is actually pretty straightforward. All we have to do is take the standard reduction potential of the cathode and subtract the standard reduction potential of the anode. So in the case of our example here, this, because it's the oxidation, this is the anode. Here we have reduction occurring, so this is the cathode. So cathode, 0 volts, minus anode, minus negative 0.76 volts, gives us positive 0.76 volts. And that's what we see here. Because we're subtracting a negative number, we end up with a positive 0.76 volts. So, sign conventions here. Well, it's not really a convention at this point, but just so you know which is positive and negative, which one is spontaneous. Positive cell voltages are spontaneous. So, just to go through the ones we've seen up to this point, if you had delta H values that were negative, those were spontaneous. Delta G values that were negative were spontaneous, but cell voltages that are positive are spontaneous. So you will have to remember that. Positive cell voltages are spontaneous. Negative cell voltages are non-spontaneous. And one other thing I want to point out here before we move on is that if we had a situation where our half reactions had been multiplied in the balanced chemical reaction, and we didn't have that here, these two things balance out just fine. We have 2 electrons being transferred, 2 electrons being transferred. But if we did have a situation where maybe instead of having zinc going to zinc 2 plus, if we had zinc going to zinc plus, for example, and so we ended up having to multiply this by 2 to get the same number of electrons being transferred, you would not multiply the cell voltage, or the standard reduction potential, by 2. You take the number straight from the table. No multiplication by anything ever. You will never take one of these cell voltages and multiply it by some value from the balanced chemical equation. It will never happen. You will simply take the number from the table and use that. The reason for this is, again, going back to that waterfall analogy, the two sides of our cell, the two half reactions, are like the height of the waterfall. So we have, the manganese oxide here. That's the top of our waterfall. And we have, although actually that would be the bottom of our waterfall. But anyway, it's just for the sake of examples here, we have iron down here. So this is the height of our waterfall, is this distance. Having twice as much iron react does not change the distance between these two half cells. All it does is it means that twice as many ions are going to move from one side to the other. But it doesn't actually change the distance between the two. And that is all the voltage is dependent on, is what is the chemical potential difference between the two. And having twice as much stuff react doesn't change the potential. It just changes the number of electrons that you have moving. So we never ever multiply these numbers by any coefficients we find in the balanced chemical equation. We simply take the numbers out of that table. All right. I think we'll pick up here with this example in the next video, so I will see you there.